Assalamu alaikum and welcome to Zaamin's Kaavish 2 midterm evaluation video. To begin with, let's first understand what today's video will cover. We will start with an introduction and a recap as to what is Zaamin and what its primary focus is. Then we'll move on to a working demo to showcase the current status of all of the integrated functionality that we have prepared for you today. After the demo, we'll discuss regarding the feedback that we received from the previous evaluation and how that feedback was then implemented. We will then move on to updates regarding the system overview, machine learning, as well as the technology stack aspects of Zaamin. We will then finally wrap up by discussing the remaining work that we have to do until the final evaluation at the end of the semester. So let's begin. Zaamin is a robust AI-based video analytics platform that focuses on 4 key aspects. The first one being real-time performance, the second being object-focused, the third being alert-based, and then finally fourth being easily deployable. All of these aspects allow Zaamin to make any security or surveillance camera into a tool for real-time insights into whatever is going on in the video frame. To showcase the current status of Zaamin, here is a guided demo. In order to start passing through our video source into our dashboard and model, I will first start the Flask application. Once that is done, we can see our dashboard is all lively and set up, showing us lots and lots of information to learn something from what we're looking at. Currently, as you can see, the video stream that we're using is actually CCTV footage from a mall. And even something as simple as that scenario, Zaamin is able to provide lots of insights using analytics that our models are producing. In this first video stream, we can see bounding boxes on persons that our machine learning model detects. This is all being done in real time to ensure top-notch performance and up-to-date insights. Right beside it, we actually see a heat map being generated similarly in real time. This heat map will allow us to understand the concentration of people in the given frame. And over time, we will see how the colors change based on where there is the most movement and most number of people. Next up, right beside the heat map, we see 2 more metrics. The first one being that of people capacity. This is really helpful in cases where people capacity management, specifically during times of COVID, is very important. And here, our dashboard allows for people to set limits, and once a limit is crossed, for example, in this dashboard, the limit is 15. Once that limit is crossed, an alert is generated so that the user can be aware of these infractions and take necessary precautions accordingly. Right below the people capacity, we also see the average footfall per minute. This helps us gain an understanding of how many people have been coming across the video frame in any given minute. Right below the prediction video, we see that there is a chart that graphs footfall for every 5 seconds for the last 1 minute. And beside that, we see that an FPS counter helps make sure that we can see at a glance whether our model and our dashboard is performing in real time. In the final row of the dashboard, we see that the first table is historical data, and this helps us keep track of all of the predictions that have been done by our models along with all of the tabulations done thus far. Beside that are 2 graphs that historically plot out the frames per second performance as well as the individual frame latency, which covers the total time taken from the input to the pre-processing to the inference step to the post-processing and finally to the rendering of the frame that we see in the videos above. And it is our optimizations that allow all of this to happen in less than 150 milliseconds, allowing us to produce amazing insights in real time. And that's basically it for Zaamin's demo. Let's move on to feedback from our previous evaluation. With regards to the valuable feedback received from the Kaavish committee during our previous evaluation, there were 3 main takeaways. The first one being decreasing the focus and scope of non-functional requirements, as last time around they were very extensive and somewhat unrealistic. The second feedback was actually increasing our focus on showing numbers and data to prove the claims that we have been making about Zaamin thus far. And then finally, one of the more important feedback was increased cohesion in the demo that we show, so that everything that is seen is actually integrated and implemented. In terms of how the feedback is implemented, we'll see that we reduce the scope of our non-functional requirements to make it more realistic and in line with our claims. Secondly, this presentation will include extensive amounts of data and metrics pertaining to our dataset, our model performance, as well as any storage savings that Zaamin will be making. And finally, to ensure cohesion in the prototype aspect, we have ensured that the demo that was just shown has all features that are integrated and functional into a single dashboard. Now, going back to our previous non-functional requirements that we used to have during Kaavish 1. Here, we see a total of 6 different requirements. But based on our evaluation feedback, we have now reduced it down to 2 core non-functional requirements with a focus on privacy and performance, and we'll discuss how the system design facilitates these 2 aspects. But before that, we'd like to first discuss on how our further presentation is broken down based on Zaamin's design. The first aspect we'll discuss will be the system overview, which will have a quick overview of the overall system design of Zaamin. Next, we'll move on to a section titled Machine Learning, where we'll include all machine learning model related progress in terms of dataset creation, model performance, as well as any optimizations that we'll be doing. And finally, we'll discuss our choice of technology stack along with the rationale as to why we chose it. Starting with the system diagram, here we can see that given a video input, the video is encoded and then passed on through machine learning models depending on the user configuration. Once the models produce their predictions, those will be aggregated and then stored into a database. The database is then called upon by our dashboard, which will use all of that data produced by the models to provide visualizations and thorough analytics to be used as insights by our users. If there are any conditions or rules set for the data, alerts will be generated accordingly. In terms of how our system design connects to the non-functional requirements, first we'll discuss privacy, where to ensure that user data is not compromised, our models do not store any video that we process. Instead, we only store model prediction metadata, which then thereby makes all private information inaccessible to Zaamin and its admins. This then also means that for every 10,000 frames, our platform right now only requires 3.08 MB worth of storage for all of the metadata related to latency, bounding boxes, and object counts. So ensuring privacy also helps us on saving storage space as well. Moving on to performance, we are utilizing all the latest advancements in machine learning model and pipeline optimization. Things like model compression, multi-threading, and utilizing high-speed read-write databases. All of this to ensure a real-time experience for our users so they can gain better insights into their videos even faster. Now we move on to the machine learning aspect of our update. First, we'd like to recap with the model details of the model that we're currently using as a backend for all of Zaamin. The architecture is YOLO, where primarily it is used for object detections and localizations. We tested 3 different variations and decided that YOLO v3 was the best model of them all due to its extensive support and compatibility with various frameworks and runtimes. The primary labels that we use YOLO to detect are either person or 6 different vehicle types. While the person model works really well, we noticed that we will have to create our own dataset to enable localization because Coco, the dataset that YOLO is often trained on, does not have pictures from a Pakistani local context, especially with vehicles like rickshaws and chingchis and bikes that have double and triple the amount of people riding on it. This is why we will need to create our own dataset and then retrain a YOLO model with that dataset. So we then set out to create the whole dataset ourselves by manually sourcing and annotating images by using a software called Label IMG to get examples that are often not found in datasets available across the internet currently. In order to solve for the issue where we have limited number of images for all of the classes that we're trying to train for, we used image augmentation, where each base image was augmented 4 times using a mixture of shifting, scaling, rotating, flipping, and also increasing and decreasing brightness and contrast by a random variable. Because of all of those techniques, our current dataset for vehicle detection includes a total of 4,400 annotations from 6 different types of vehicles. And after our augmentation process is complete, our training dataset will nearly quadruple in size to almost 15,000 total annotations. To allow for local contextualization of the vehicle detection by YOLO, we will be using transfer learning. And here, as we can see in the summary, the average losses actually relatively converge right after 40 or 60 epochs. Besides the graph, you can see all of the initial parameters that we used, including the weights that we used as an initial starting point, along with the width and height of the frames, which is 416 by 416. Beyond just the training step, we also focused on optimizing 2 variations of YOLO v3 by using quantization, which allows us to reduce the precisions of the weights from 32-bit to 16 bits. And as we can see, we not just saw significant space savings, which is nearly 50% of the original size, but we also see an increase in the mean average precision for both the models. For the YOLO v3 normal size model, we see an increase of nearly 7%, where the tiny YOLO v3 model also sees a similar gain of nearly 6.6 percentage points. This showcases how model optimization could end up not just saving storage, improving latency, but also detection accuracy as well. Now we move on to the discussion of the technology stack that we are using. But first, to set the stage, we'd like to discuss the technology stack that we were previously using, which primarily relied on NVIDIA Jetson with an application built on a React and Electron frontend, utilizing model optimizations by both Neural Magic and TensorFlow. Now we can see that we primarily rely on Intel's OpenVINO toolkit as the primary runtime for our machine learning models, which are then run on a Flask web app supported by Grafana and InfluxDB, where the models primarily are either using PyTorch or TensorFlow. And as to why we made these changes, the first was a lack of platform agnosticity. Our reliance on NVIDIA's Jetson SDK made sure that we could not utilize anything except for NVIDIA hardware, which leads us into our second problem of hardware inaccessibility. Because GPUs are so expensive and difficult to find these days, our optimized code did not have any hardware to actually run on. And finally, on top of it, all of the previous technology stack made it very difficult for us to try different variations of different models, different configurations, and different parameters. Which is why we rely on the current technology stack we just mentioned, because it allows us to be platform agnostic, allows us to run machine learning models right on the CPU in the most optimized way possible instead of having a requirement for a GPU, and then they also allow us the flexibility to experiment with lots of different things and lots of different configurations. So with all that done and dusted, we now need to discuss as to what remains till the end of this semester and of Kaavish 2. We primarily have to do further model training and testing for our local contextualization, and once that is done, we will be optimizing the models further to get improved performance by utilizing quantization and hyperparameter tuning. Finally, once the model is ready to go, we will deploy the vehicle detection model in our dashboard, the framework and the foundation of which is already set and is working really well for our person detection module already. Finally, we will add line and zone-based filtering of the detections when we deploy the vehicle detection. And once all of that is done, we will have completed Kaavish 2 with the promise of presenting Zaamin as a fully fledged real-time video analytics system that is primarily focused on person and vehicle-based object detection with deep insights and analytics related to it. Thank you so much for taking out the time to watch this video, and we hope you have a much better understanding of how far Zaamin has come since just the start of Kaavish 2. Take care and Allah Hafiz.